Okay, so let me share my screen. Let's start. Okay, so what I'm going to be talking about today is optimization. More precisely, I'm going to start setting up some groundwork so we can speak about optimization. And deep dive into optimization and how it's related to machine learning. The reason optimization is very much related to machine learning is that many times the end result of a machine learning problem is an optimization problem. So many times you need to minimize some function given some constraints on the function. So the points are coming from some set. Okay, so many times that's what you need to do in order to solve a machine learning problem. For instance, for a neural network, you use gradient descent and you minimize the loss function. So that's what you need to do. So a better understanding of minimization problem and how you solve them is helpful for machine learning. And today I'm going to start laying some basic groundwork so that we can understand, comprehend things that have to do with optimization. Okay? And look at the different algorithms like a gradient descent, Newton method, and all other kind of algorithms that we use in machine. So the basic thing I want to speak about is basically when a function is bounded. So the basic question that I want to visit or understand is when a function is bounded. So in general, I'm talking about a function that has a domain. Domain is some set, and then the range is the real numbers, just numbers. Okay, so you have a function that goes from some domain to the real numbers, and what I want to know is when the function is bounded. So there's some number, there's some number m, so that f of x is less than m for all x in A. Okay, for all x in the domain, function is less than m. So for instance, let's take a few examples. This is a function. This is a function, and this is a function. So the first function is bounded or not?
First
function
is bounded. As it is dividing the 1 and always be less than 1.
So the first function looks, if maybe you're thinking about I'm thinking that the domain is the entire set of numbers. So the first function looks like that. If I'm not mistaken, I think it looks like that.
Yeah.
So this is a so look at the drawing at the graph again. Is that function bounded?
Fx equals 1 by x. That means it's not it is not touching the baseline, right? It will be never ending kind of a parallel, it will be going. So there is no boundary.
There's no boundary. It goes up and up and up. Okay.
Yeah. Till infinite. Okay.
So this function is not bounded. This one is not bounded. What about this one? Is this one bounded?
It is x into 2 or x to the power. It is x into 2, right?
No, x to the power of 2. Thanks. X to the power of 2. Not bounded?
So
Not bounded, right? That is also not bounded.
Not bounded. Okay, and what about this one? Is this one bounded?
Yes, it should be.
Yes.
should be.
Yes, bounded. Okay, so some functions are bounded, some functions are not bounded, and what we want to understand is when functions are bounded. The reason is that so if we go back to this drawing here, okay, so as we go nearer to 0, or any domain that is around 0, we won't have a maximum value here because the function is not bounded. Okay, so the function is the function that is not bounded typically would not have a minimum or a maximum, so we would not be able to solve it. So we will not possibly would not be able to solve the maximization, the optimization problem. Okay. So, okay, say if you look at the function between 1, say between 1 and -1. So the function here is so if I draw a line here, then I need to kind of stop and then go to the other side, so to speak, and then draw the line, right? So the point 0 is a point of the function being not continuous, okay? So one of the things that we want from functions in order that we can solve the optimization problem is that the function will be continuous. So essentially that means that the function is, we don't need to pick our hand from as we draw the function, we don't need to pick our hand. We just from the paper and then put it back. Okay, conceptually. So let me. So let's go over this function again. 1 over x, is that function continuous or not?
1 by x.
Yes.
Continuous means like continuous means like kind of it will give same interval after like if I increment x, the function will be incrementing in the same interval. Does that mean continuous?
Continuous means that if you draw the function, you don't have to pick the hand from the paper as you're drawing it. So this is a continuous
okay.
function.
Di-
Okay.
Oh, discrete, not discrete. You are telling. Okay, okay.
But
Okay.
this is not continuous. You see, I'm going like this. Then I pick the hand.
1
then,
0 1 0. Yeah.
Okay.
So 1 by x is obviously continuous.
No, it's not, because I have to pick the hand when I go from here to here. I have to pick my hand from the paper and then put it back. Okay.
Yeah, because it's not defined at x is 0.
Yeah, exactly.
That creates a
Okay.
hole.
Okay. When x is 0. Okay.
Yes, yes. So there's one point in which it's not continuous. Just
Right.
okay.
Great. Okay.
Make sense now?
Yes.
For instance, if you look at this function, so this function is now I'm going. This is 1. This is 2, and this is 1. This is 2. Now what I'm doing is I'm drawing the line here. You see, this is the function. So it's like a step function. Now I need to say what is happening at the connecting points. So the function is going to be 2 at 2, and okay, so same here. It's going to be 1 at 1. Okay, and here so there's a jump. Okay, I'm going like there's a line, and then I jump to here. I need to pick my hand from the paper and then put it back, draw the line, then jump. Pick my hand from the paper, put it back, and draw the line. Okay, so this function is not continuous, right? Because I need to pick my hand and put it back. Okay, make sense? How many non-continuous points do you have in this function?
In 1 by x? One is that 1 by 0, which you told like it will be infinite.
Yes, one is not a point where it's not continuous. 2 as well, right? And then I keep going, right? I go, this is 4. So I do another one here, okay? And so on. So how many points are not continuous?
Infinity.
Yeah, exactly. So there's an infinite number of points which are not continuous, because for each time I do this step and I jump, okay? So I go between 0 and 1, and then I jump between 1 to 2, and then I jump between 2 and 3, and then I jump, and so on. Okay? Make sense?
Yes.
Very good. Okay, so basically I want to understand when a function is bounded, and we will need the idea of continuous function, and basically the answer is going to be that if A is why did that change? If A is compact, and I'll explain what compact is, and if the function I'm talking about is continuous, then the function is bounded. So there's a very general way of thinking of when a function is bounded. Whenever the set we're starting with is compact. Okay?
Where A is compact, what does it like actually sensing it to make it A is compact? On an actual sense, I'm asking.
Yes.
A
That's
is compact.
correct. So I need to explain now what does it mean that A is compact. Okay.
Okay.
So let me explain what I mean by that. So the first thing to understand, well, okay. So in order to explain what does it mean that A is compact, I need to explain what a topology is. Okay. So a topology is a set of sets that are called open. So we have a set of sets B B alpha, BA. Okay. There could be many sets of those sorts. They're all called open. And so that a union, I'll explain in an example. Union of the open sets is open, and finite intersection is open, and they include the entire set and the empty set. Okay, so that's a topology. Let me start with an example. Okay, so if you think about the numbers. And think about sets that so that for each x in A, there is x minus some number, x plus some number that is included in A. Okay, so that means, in other words, all of the numbers z such that z is bigger than x minus e, and z is smaller than x plus e are in A. Okay? So let's check if we understood what an open set is in the example. Consider all of the numbers between 0 and 1, not including 0 and 1. Okay? So is that an open set? Let's think about it. So let's go back to our drawings. So we're looking, this is the line. We're looking at the numbers between 0 and 1, not including 0 and 1. Okay, all of these numbers. Between 0 and 1, not including 0 and 1. When we take some point here. So this is a point X. Okay? Now, can you tell me what E could be so that the entire segment around X will be included in 0 and 1? So I need to take an E that is
Any
odd. Mhm.
So as per the definition you said that there should be a number, for example, E, for example, 1. So all the numbers.
One will be too big because one.
Sorry, yeah, 0.1.
One will include all of this, and it will not be included.
Correct. We can go with 0.1 or something. So
Yes.
X minus 0.1 and X plus 0.1.
Yes.
So
So
all the numbers.
Right. So if you take X, like if we take X plus 0.1 and X minus 0.1. So all of the points between these 2 points will be included in the segment 0, 1. Okay?
Correct.
So this shows that segment 0, 1 is an open set. Okay?
Right.
Very nice. Now, so if we take so this is an example of a topology, and we still need to understand why this is this is the standard topology on the numbers, and we need to understand why it's a topology. Okay. So let's check if it's a topology or not. In order to check that it's a topology, we need to see that that the union of open sets is open. The intersection, the finite intersection of open set is open, and that it includes the entire set, and it includes the empty set. That's what we need to check. Okay. I won't do everything now. I'll just do a quick check, just so you can get the flavor of how you check it. So let's check. Let us check that the union of open sets is open. Okay. So we take so if so we have a set that is the union of I'll write it over here. It will be easier to understand. I'll write it over here. So say that A alpha is open. This A alpha is a set of open sets. And now we look at the union of A alpha. The union of these sets, okay? Now, what does it mean that a point, we need to take a point in the union, and we need to show that there's a segment around that point, right? So because the point is in the union, what does it mean? What can you say about the point if it's in the union of these sets?
That means it may be in both the sets common, or it may be either of it.
Right, but this is an infinite number of sets, but it means that X is in some set, exactly as you said. Some set, as you know, we'll call it alpha 0. And because we know that X is in alpha 0, there is a segment X plus E X minus E is this segment, okay, that is completely included in A alpha 0. Correct? Because we said that all of these sets are open. Okay? So what can we say about this segment? That it's included in what?
This is a open segment.
Yes, so the open segment is included in A alpha 0. So it's also included in what? If it's included in one of these sets, what can you say in addition to that?
Union.
Yeah, it's included in the union.
Right. And if it is in both the sets, then it is an intersection.
No, right, but because it's we know that it's included in one of them, then it's included in the union. Okay?
Okay.
And that means that the set is open. So the union is open as well, you see. So we prove that the union is open.
Right.
Okay. So we did an example now, and now I'm ready to tell you what compact is. So remember, we were trying to see what that means. If it's a compact set, if A is compact, and the function is continuous, that means we don't pick our hand from the paper, then the function is bounded. Okay? So now I'm ready to explain that what compact means. So compact means that if let me go back here. Okay, so if A is covered by a set of open set, so if A is covered by a set of open sets, then compact means that there is a finite set that already covers A. There's a finite set that already covers it. Okay. So that's compact.
So okay, can we repeat that last this one? That if we are saying that union of A alpha is union of A, then
If you have infinite sets A alpha, and their union is A, includes A, then there's a finite set that already includes A. A finite set A1, A2, AN that includes A. Okay. So for instance, I'll show you an example. Like if you think about the following open intervals, I'll write them a example. Okay. If you think about the following open intervals, minus n, n. Okay. So the set minus n, n, so that n is a natural number. So for instance, we have here the segments minus 1, 1, minus 2, 2, right? Minus 3, 3, and so on. It's an infinite number of sets. Do they cover all of the numbers?
Yes, because they are covering all the reciprocals, that means negative and positives of all the numbers.
Yeah, right. So if we let's call this a AN. Okay, this is the set AN. I don't want to call it A. I'll call it B. Okay, so B covers. I wonder if there's an undo. Otherwise, I'll write it. Yeah, nice. So B covers R, covers all of the numbers, and in fact, and you can think about intuitively, but in fact, there is no finite subset of B that covers R. Okay, because if you take there's no finite subset of B that covers R. If you take a finite subset of B, then it will only cover, like if you take, minus 1, 1, minus 2, 2, minus 3, 3, it will only cover up to 3. It won't cover the entire line. Okay? So if you think about it a bit, there's no subset that cover subset of sets in B, finite subset of set of B that covers R. And in fact, R is not compact. But we didn't show it here, but it's not compact. Okay, so what we did today, we understood what is this claim, basically. That was the purpose of today's meeting. So we understood that if A is a compact set and F is continuous, then the function is bounded. Our purpose was only to understand the claim. Hopefully you got some understanding of what the claim is, and we'll continue next week. Okay? Great. Thank you very much for joining.
Thank you. Thank you, Eitan, just one question I would ask. Like, to implement, like, to get more out of this thing, and like to do something practical on this, can we refer anything, like, to study it more?
Yes,
The
yes. There's a lot of good resources about optimization, like lectures and so on. I'll send a pointer.
Thank you. Thank you.
I'll share with everyone a pointer on a lecture on optimization. Okay?
Yeah. Sure.
Okay. So thank you very much for joining, and thank you. We'll continue next time.
Yeah.
Thanks, Eitan.